Welcome to Chapter 30, Fiber Optic Cable. Fiber optic cable supports transmission rates over 1 gigabyte per second. Or 1 gigabit per second. It's primarily used for network backbones and long distance runs. Fiber optic cable consists of glass or plastic core that carries pulses of light. The pulses of light represent binary data. A pulse of light represents a binary 1, and the absence of light represents a binary 0. A transmitter at one end and a receiver at the other end convert from electrical signals to light and back. There are several reasons for fiber optic cable might be chosen over copper core cable. It provides better data security. It's almost impossible to tap into it. It's immune from electromagnetic interference, noise. It's lightweight and small in diameter. It's fairly safe to work with. There's not electricity on it. It has a very wide bandwidth. It is corrosion and water resistant, and it supports data transmission over very long distances. Now, light is a form of energy that's closely related to electrical energy, and for the purpose of this class, we'll consider light as a wave and not a particle. Light is classified as electromagnetic energy and is identified in the electromagnetic wave spectrum chart along with radio waves, X-rays, and gamma rays. An electromagnetic wave is a form of energy that behaves like a wave and can travel through a vacuum. In copper core cable, electrical energy wave patterns were described using the term frequency. Light energy can also be described using the term frequency, but the preferred term is wavelength. Wavelength in relation to light waves is the distance of one complete cycle and is measured in meters. Three common wavelengths for fiber optic communications are 850 nanometers, 1300 nanometers, and 1550 nanometers. Fiber optic devices and cables, such as transmitters, receivers, and fiber optic core diameters, are selected according to wavelength of the signal used. At these wavelengths, there is much less signal loss. Fiber optic cable is composed of a glass or plastic core surrounded by cladding. The glass or plastic core is the medium for transferring light waves. The cladding surrounds the core and causes the transmitted light to remain inside the core. A buffer area surrounds the cladding and core. The buffer is wrapped around the core and cladding to provide physical protection. In addition to the buffer area, waterproofing materials are sometimes inserted under the cable sheath. The sheath is similar to the insulating jacket on copper core conductors. Its composition depends on the environment in which the fiber optic cable will be installed, and the size of the fiber optic cable is expressed in micromils. Fiber optic cable carries light and not electrical energy. A new set of terms is needed to describe the characteristics of light carried over fiber optic cable. While some of the terms might be familiar, some new terminology that is unique to light is also introduced. The first characteristic presented is attenuation, which is the loss of signal. The major cause of attenuation in fiber optic can be characterized as scattering, dispersion, extrinsic losses, and Fresnel reflection loss. Attenuation is expressed in decibels or decibels per kilometer. Scattering is the loss of signal due to impurities in the core material. No core material can be made 100% pure. A microscopic amount of impurities will always remain, and these impurities cause the light to scatter. And the longer the distance, the more scatter there is. Glass core is a better transmitter of light than plastic, but it is also much more expensive. To reduce attenuation, glass cores are used on very long runs of fiber optic cable. Dispersion is the distortion of the light wave pattern as it reflects off the core cladding. Dispersion is the main factor that limits the maximum length of fiber optic cable as used as a communication media. Extrinsic losses are caused by physical factors outside the normal core. Physical factors can be splices, connectors, and bends in the fiber core. Splices in fiber optic cable need special attention. Splices, couplings, and connectors are the main reasons for signal loss in normal runs of fiber optic cable. Signal reflection loss commonly occurs at connection points in fiber optic cabling. It is typically due to the refraction property differences in the core material, the connector material used for sealing the connector, and air. Light waves traveling from one type of core material to another cause signal loss. Broad classifications of fiber optic cable based on the diameter of the core are multi-mode and single mode. In general, multi-mode fiber optic cable has a larger core diameter than single-mode fiber optic cable. A larger core diameter causes more light loss due to dispersion. Single-mode fiber optic cable is much smaller in diameter than multi-mode. The diameter of single-mode fiber optic cable is almost equal to the length of the light wave traveling through the cable. Because the core is designed to closely match the wavelength of the light wave cannot readily disperse as it does in a larger diameter core. The result is single-mode fiber optic cable can carry light farther than multi-mode fiber optic cable. In the 1990s, the IEEE amended or modified the 802.3 Ethernet standard to include gigabit Ethernet. The amended standard is known as IEEE 802.3Z. In 2002, the IEEE amended the 802.3 Ethernet standard to include 10 gigabit Ethernet. The amended standard is known as IEEE 802.3AE. This standard only recognizes fiber optic cables. 10G base W is a collection of cable standards such as 10G base SW, 10G base LW, and 10G base EW. The W in the 10G base W standard represents a wide area network. When the W is used in reference to a specific standard, such as G base SW, the W represents wavelength. For example, 10 G base SW represents 10 gigabit short wavelength. Fiber Distributed Data Interface, or FDDI, is a standard developed by ANSI that employs fiber optic cable over great distances. The distances can reach as far as 40 kilometers and support data speeds of 100 megabits per second or higher. FDDI is used mainly as a backbone for large network systems, such as a metropolitan area network or a wide area network. FDDI is structured as a pair of rings, 2 rings of fiber optic cable connected to each node on the network. Using FDDI guarantees continuous communication because if one ring fails, the other ring automatically takes over and provides the path for communication. Let's look at some common fiber optic connectors. There are many different kinds of fiber optic cable connectors. Some are proprietary, some are not. It is best if you use connectors from the same manufacturer when installing a new fiber optic network or extending an old one. The most common styles of fiber optic connectors are SC, ST, FC, LC, and MTRJ. The ST connector is round and uses a push and twist connection similar to BNC. The SC connector is square, uses retaining clips to hold its position. Sometimes the two SC or ST connectors are fabricated into a single unit and generally referred to as duplex connectors, which means the single connector is referred to as simplex. The FC connector is designed with screw threads as part of the physical design. They're very similar in design to coaxial screw-on connectors. The LC connector is a relatively new standard developed by Lucent Technologies. The LC is classified as a small form factor connector. The term form factor refers to the physical attributes of a connector. The LC connector is approximately half the diameter of an SC or an ST connector. The MTRJ connector is unique in design because it incorporates two fiber optic cores into one assembly without the use of a clip. It is always considered a duplex connector. The MTRJ is also a small form factor connector. Now, there are a few even newer styles coming out, and I imagine there will be new ones tomorrow. Remember to keep calm and document everything.